Hello, everyone. Welcome to the EVO seminar series. Our guest lecturer today is Dr. Patrick Forber, and he's going to be presenting on some interesting definitions or innovative, changed or elaborated, some adjective definitions of altruism and spite and selfishness and the various terms that evolutionary biologists use to talk about social interactions. And with that, I will give it to Dr. Forber.
Thank you. Thanks very much for inviting me to participate in this virtual seminar. First time I've done a virtual lecture, so it's kind of exciting. William Hamilton was rightly lauded as being incredibly influential in thinking about social behavior, right? So his early papers in '64 sort of set the problem and provided a solution for the evolution of altruism. And much of the subsequent formal work is really following on in Hamilton's tradition. In those early papers, he came up with a kind of classification scheme for social behavior that's been enormously influential, right? And what I want to do today is reevaluate that scheme. I think Hamilton had a great insight, but it's sort of limited. And when we take a sort of broader perspective on social interaction, we can get a richer perspective about what social behavior is and what role this kind of classification scheme is supposed to play, right? So let me just start with a quick refresher on Hamilton's perspective on the evolution of social behavior. So he had a straightforward view that you want to think of the effect of the behavior on both the actor and the recipient. So the idea is that there's some actor out there and he's going to behave in a certain way, and that behavior is going to have an effect on the actor's fitness and on the recipient's fitness. So when a parent provides food to their offspring, or when I try to help out a friend, I am taking a risk or paying a cost and giving a benefit to another, right? So it can have a positive or negative effect on the actor and a positive or negative effect on the recipient. If it's both positive, you might call that mutually beneficial behavior, right? Both of us benefit. This isn't presenting a particular evolutionary puzzle. It's in my interest, it's in your interest. Similarly, if it's beneficial to me but harmful to you, Hamilton called this selfish behavior. Think about theft, right? No evolutionary puzzle associated with this. You do worse, I do better. That sort of behavior would be favored by natural selection. The puzzling behaviors are when they actually cost something. So when the actor has to pay a cost in terms of reproductive success or fitness, right, that's where it gets sort of puzzling. If I pay a cost and you benefit, that's altruism. If I pay a cost and you're harmed, that's spite. Hamilton was really worried about altruism. He wanted to know how this kind of self-sacrificial but beneficial behavior might evolve. He later came to appreciate that spite could evolve too, primarily through his interaction with George Price, another sort of polymath and theoretical biologist that was doing some work around the 60s and 70s. He's got an equation named after him, the Price equation. He and Hamilton collaborated a bit, and it was through that collaboration that Hamilton came to realize spite was a thing. I've got a lot to say about that. We can talk more about that in the question period, but I'm going to put that aside for now and focus on Hamilton's favorite behavior, altruism, right? So this is a special class of behaviors, and there's a whole legacy of formal work exploring how altruism could evolve, right? So let's look at it from a game theoretic perspective. So we can construct a game that's a good representation of altruism. A game is where we have two individuals that are interacting and both can play a strategy, right? And the strategies determine the payoffs we receive. So we could play an altruistic or selfish strategy, right? If both of us are going to play the altruistic strategy, we both receive some benefit B, but we pay a cost C to confer that benefit on our partner. If I am selfish with an altruist, I receive a benefit. If I'm an altruist with a selfish person, I pay a cost, but receive nothing in return. Selfish individuals simply break even. So this is a nice way of representing altruism. This is known as the prisoner's dilemma in game theory. So it's one sort of two-person game. Do people know the prisoner's dilemma? Is this a familiar term?
Yeah.
It would be good to go over it.
Okay. All right. We'll come. So I'll mention more about the prisoner's dilemma in a second. But this way of setting up altruism is a prisoner's dilemma in effect. All right. So look, you can see why this is puzzling. Because if I'm playing an altruist, I should be selfish. B is greater than B minus C. If I'm playing a selfish person, I should be selfish. 0 is greater than negative C. So selfish behavior should evolve. The way you can represent this is you've got two strategies, and we can draw what's called a simplex. So this line is going to represent the proportion of A's and S's in the population, right? The proportion of altruists and the proportion of selfish types. So there's just two strategies, so they have to add up to 1. So if you're over here on top of the A, there's 100% altruists. If you're over here on top of the S, it's 100% selfish. If you're somewhere in between, there's a mix. So the midpoint's 50-50, and so on. In this scenario, right, what you see is that no matter where you are in the population, it's always better to be selfish. So natural selection is going to push you towards all selfish, right? So you've got this open circle here, unstable equilibrium. You introduce one selfish type, so you move off the end, and selection is going to push you to 100% selfish. So altruism should never evolve under standard assumptions. What Hamilton did is say, hang on a second, maybe there's a way we can tilt the field in favor of altruism, right? So this system that I described here sort of presumes that we interact at random. If I don't know who I'm playing against, I should defect. I should be selfish. But suppose altruists could find each other. Suppose they had a signal, a secret handshake, a high five, something that they could use to signal that they're both altruists. And then they could cooperate. So if the altruists can find fellow altruists and exclude the free riders, altruism can evolve, right? So what Hamilton thought was that, hey, look, maybe we can change the scenario a bit. All right, so I'm going to throw some equations on the board, but they're pretty simple, right? It's just some fitness functions using this game as a backdrop. So we want to know the fitness of the altruist in the population. And we want to know the fitness of the selfish type in the population. I'm going to simplify these a bit. And let's say we're going to have this variable x. That's going to be the frequency of altruism. Okay?
You've lost you on the board. That's fine.
What's that?
If you shift your screen slightly, we'll be able to see. Aha.
I can also move this over. All right. So is this the edge right here?
Yeah, just about right there. Yeah, you've crossed it.
Okay. All right. So if we're thinking about an altruist in a population where you're going to meet each other at random, there's a probability X of running into a fellow altruist. That's how frequent they are in the population. So if I'm drawing at random, I draw an altruist with probability X. So if I'm an altruist, with probability X, I meet a fellow altruist and reap the benefit, but I always pay the cost because I'm an altruist myself. So I'm always paying the cost, but with probability X, I run into a fellow altruist and receive the benefit. The selfish type, with probability X, runs into an altruist and receives the benefit, but never pays the cost, right? So bx is greater than bx minus c. So that's why you get this kind of dynamical representation for the problem of altruism, right? So Hamilton's idea was that, hey, hold on, let's not presume random mating or random interaction, sorry. Let's presume that individuals can have a positive probability of finding a like individual. So altruists can find altruists a bit more than chance, right? So let's introduce a factor R, right? And that's going to be the probability of pairing up with someone that's the same as you, right? And we can use this probability R to change these fitness functions. So instead of bx minus c, what we're going to have is R times b minus c. So with probability R, I find an altruist and we both get b minus c. Otherwise, we pair at random, right? So that's just this is the random fitness, and this is the chance I meet an altruist and get b minus c. With the selfish type, with probability R, I interact with another selfish person, and that's a 0. With 1 minus R, I interact at random, and I have a chance to meet an altruist, right? So notice what we've done here. What we've done is we've put our thumbs on the scale a little bit. You've got this 1 minus R discount on the random pairing fitness, and then the altruists get a benefit because they help each other out, but the selfish type doesn't because they go their separate ways. Now, if you set this up as an inequality and you ask, when is this fitness function greater than that function, you can do some pretty simple algebra and get a version of Hamilton's rule. This factor R needs to be greater than the ratio of cost to benefit, right? And that was the solution to the evolution of altruism, right? So if a behavior is altruistic, then there needs to be some kind of positive assortment amongst altruists, be they kin, through some sort of secret handshake or signal. Some way you need to positively correlate altruism with altruism, and you can get it to evolve, right? And the magnitude of the costs and the benefits are going to determine what the magnitude of R needs to be to get the evolution of altruism. Okay. Is that clear? Any questions so far?
So is this R, this is a different R from relatedness? I mean, they're related, but they're not the same.
Well, I would say this is analogous to relatedness, right? So the way Hamilton set it up, he thought about genetic relatedness. But that was really based on the assumptions of his pretty straightforward population genetic model. This R is really just an assortment factor. It doesn't have to be genetic relatedness. Mm-hmm. Okay, if it's genetic relatedness, you've got your sort of standard kin selection model, but really it's just assorting strategies. That's what matters, right? So if we can recognize that we're fellow altruists, we don't have to be kin. The kin selection mechanism helps that we just help anyone indiscriminately. We just tend to help kin, and so the R will be higher automatically because I'm hanging out with my family. And we share the same sorts of genes, so there's a high probability we have the altruism gene, the way Hamilton set it up. But that's a very idealized model. So this is, I think, effectively relatedness. It's just a different, it's the more game theoretic way of approaching the problem.
I'd love to hear from some of the students. Anyone want to quickly paraphrase maybe what we went over so far? All right, I'll call on someone. Chris, you want to give a shot at it?
Yeah. So He's speaking about trying to understand why altruistic behavior would rise because, based on the graph to the right, clearly the values of selfish behavior are greater. So natural selection should favor this, because your personal fitness would improve the most through selfishness. But then the formula introduces the with R and with the assortment of altruists. If you remove random mating, then if two altruists are able to find each other higher than chance, then your equation shifts, because there can be a scenario where overall the fitness benefit you get from being altruistic outweighs the selfishness, and then that evolves in a population because of the values you get when R is greater than C over B.
Nice. That's right. Okay, so really a step forward, right? Hamilton developed this classification of behavior, isolated a particular class of behavior, altruistic behaviors, and then had a sort of story. It had an evolutionary problem to overcome, and he had a solution for how you overcome that problem, right? And that was sort of the story about the evolution of altruism. It's a very influential story, and even to this day, there's a lot of cool literature on explaining how you generate these positive correlations, get the evolution of this beneficial but sacrificial social behavior. Okay, so the paper I gave you guys tried to argue that there's a limitation in this approach. All right, and what I want to do is try and walk through the reasoning there, right? It's not that this is wrong, it's just limited. It's very idealized. And if we think about a broader class of behaviors, we have to sort of expand our classification system in a way to sort of understand what's going on from an evolutionary perspective. Okay, I'm going to erase the equations. Is everyone all right with that?
Yeah.
All right.
I just have a quick question.
Yes.
In the first chart, what does M.B stand for again?
Mutual benefit.
Oh, okay, got it.
I couldn't fit it in the little box, but yeah. So
okay, thank you.
Beneficial behavior. Both the actor and the recipient do better. So
okay.
It wasn't puzzling from Hamilton's perspective why that sort of behavior would evolve. Okay. All right, so we've got Hamilton's standard scheme. So what could possibly be wrong with this standard scheme? Well, let me state the problem up at the outset, and then we'll work up to how we get there. Here's the limitation. It presumes that the recipient doesn't affect the payoffs, right? So there's an actor, and the question is, does the actor behave altruistically or not? Or does it behave or interact with the recipient or not? And these costs and benefits determine whether the behavior is altruistic or something else. The recipient has no role in whether the behavior is good or bad for the both of them. So in a way, the actor is just picking a recipient and behaving towards them. It's kind of one-way street for how the fitness, costs, and benefits are determined. In social scenarios, that's not always how it happens, right? Often what the recipient does, what your partner does, matters, right? So let's think of a different kind of strategic scenario. Think of coordinated hunting, right? So monkeys do a version of this, chimps will do a version of this. Some chimps will drive the prey towards other chimps that will hang out and ambush the prey. So you need two roles. You need a driver and an ambusher, right? Or you might think about bringing down a big game like a stag. So the two of us need to cooperate to bring down the stag, but we could each go our separate ways and hunt hare. So this is a strategic scenario where how well I do depends on what you do, right? And we need to coordinate our actions to achieve the cooperative outcome, right? So let's think of a different game called the stag hunt, right? This is named after a passage from Jean-Jacques Rousseau, but the idea is about coordination. So there's two strategies. Usually it's cooperate and defect, right? And the idea is that, look, we could both defect, in which case we would both, say we go hunt hare in the story. We both do all right. We'll get a payoff of 1. We could both cooperate, in which case we bring down the big game, and we both get a payoff of 3. So we both of us would rather cooperate. So this is why it's different than the prisoner's dilemma or the problem of altruism. Now, if you go hunt hare while I'm trying to hunt a stag, I get nothing. But maybe you have an easier time hunting hare. All right, so the first number is the payoff to row player, and the second number is the payoff to column player, right? So if we both cooperate, we both get 3. If I defect and you cooperate, you get nothing, but I get 2. We both defect, we get 1. So you can see why this is a coordination game, right? We both want to do the same thing. If you're defecting, I want to defect. If you're cooperating, I want to cooperate, right? So there's no longer the dominant always be selfish option. No matter what my partner does, I do better by being selfish. In this case, what's good for me depends on what you do. We have to coordinate our strategies in the right way.
Is there a reason why the payoff is 2 for the defect, and or when only one person defects, whereas 1 when you both defect?
There's no deep relevance to that. I mean, I could have made this a 1 instead of a 2. It's just if you do it with the 2, it makes the diagram that I'm about to draw much easier, right? Because it's a 50-50 split.
Gotcha.
So really what matters is that this is the best. Mutual cooperation is the best, right? So this is a stag hunt game, and we can use the same strategy of representing the evolutionary dynamics with a simplex. So we have 2 points because there's 2 strategies, right? And now we want to know, we can set up the fitness equations just as we would with the altruism case, right? We can pair at random, and we want to know, should I cooperate or should I defect if I'm going to meet somebody at random? Well, it turns out it depends on how many individuals are in the population playing the strategy of interest. So right there in the middle, there's going to be an unstable tipping point. If more of the population are defectors, well, then evolution is going to push us towards all defect. If more of the population are cooperators, then evolution is going to push us all to cooperate, right? So notice the difference. We've got an unstable midpoint and 2 stable endpoints, right? So if most of us are cooperating, I should cooperate because chances are I'll meet a cooperator and that pays off way better than defecting, right? So in this scenario, cooperation is stable, but it requires coordination. If we're over here, it's hard to transition to a cooperate norm. Okay, so what's cool about this? Well, look, first off, it's about coordination, and it doesn't have the same subversion problem that altruism faces, right? So this is about cooperation, but it's not altruism, right? Second, how well I do depends on on what you're going to do, right, in our interaction. If you cooperate, I should cooperate. If you defect, I should defect. This scheme that Hamilton developed doesn't help us here, right? It doesn't take into account what the recipient could do. These are just whether the recipient benefits or suffers, right? It's not taking into account what strategy the recipient might be deploying in response to my strategy. Okay? So let's think about this for a second. Suppose, let's ignore this column for a second. Suppose we live in the cooperative utopia, right? Everyone's cooperating, everyone coordinates and hunts stag. It's a great population to be in. You wake up one morning and you have to decide, well, do I hunt stag or do I hunt hare on my own, right? Well, if I cooperate, my opponent would be getting 3 rather than 0. So it's beneficial for my opponent. I'll get 3 instead of 2, so it's beneficial for me. So cooperation looks like it's mutually beneficial if everyone else is cooperating. Now, what happens if I defect? If I defect, I get 2 instead of 3, so I pay a cost. You get 0 instead of 3, so you suffer. So if I defect in a population of cooperators, that's spite. I'm paying a cost to hurt you. You get 0 instead of 3, I get 2 instead of 3. So that's in the all cooperate population. Let's flip it and think about this column and ignore the cooperate column for a second. So in a population of all defectors, individuals that just hunt hare on their own, they never coordinate and try to bring down the big game, I have a decision whether to cooperate or defect. So if I cooperate, you get 2 instead of 1, and I get 0 instead of 1. Right? So I'm paying a cost of 1 to give you a benefit. So if everyone's defecting, cooperation looks like it's altruistic. I pay a cost to help you out. If I defect, well, you pay a cost because you get 1 instead of 2, and I get a benefit. I get 1 instead of 0. That looks like selfish behavior, right? In a population of defectors, defecting is selfish. In a population of cooperators, defecting is spiteful. Cooperation has the same sort of thing. In a population of defectors, cooperation is altruistic. In a population of cooperators, it's mutually beneficial. This is weird. This strikes me as really weird. The same behavior is either spiteful or selfish, depending on what everyone else is doing. The same behavior, cooperation, is mutually beneficial or altruistic, depending on what everyone else is doing. This is sort of odd that the classification of the behavior is flipping like this, depending on the composition of the other people in the population. Okay, so that's where it's puzzling. Hamilton didn't think about the recipient deploying a strategy in response to the actor. He just thought about the actor, right, and its effects on the recipient. When we think of it strategically like this, all of a sudden, whoa, all right, things are strange. So we need to revise the classification system. So we've looked at 2 games, the Stag Hunt and the Prisoner's Dilemma. And now what I want to do is put all the possible 2x2 games on one space for you and show you what's going on here. So Prisoner's Dilemma, the problem of altruism. Stag Hunt, it's a problem of coordination. Also a good kind of representation of cooperation, but a very different kind of cooperation than altruism, right? We can map all the 2x2 games out, right? And what we can do is, so this is all worked out in the paper, but you can just think of the 2 possible strategies, X and Y, and then you can map out the possible payoffs, right? A, B, C, and D. Now, the rankings of these payoffs are what going to determine what sort of game you're in, right? And so these are the details that I go into in the reading, right? So when A is greater than B, but D is greater than C, you're in a Stag Hunt. When both B is greater than A and D is greater than C, you're in a Prisoner's Dilemma. But there's other games too, right? It could be that A is greater than B and C is greater than D. We call that the Prisoner's Delight, where cooperation is the dominant game. And it could be that A is greater than B, but D is greater than C. And then you're in a game of conflict, known as the hawk-dove game, or it's called snowdrift or chicken, depending on what literature you're in, right? So we can look at how these payoffs compare. And that's where figure 1 comes from in the paper, right? It says, well, let's look at the vertical axis of C minus D, and the horizontal axis for A minus B, right? And we can have -1. Okay, so we've got the 0, 0 point is here, right? So if we move into this quadrant, we have a dilemma. All right, over here we have a delight.
And could you explain why the axes are C minus D and A minus B?
Sure, I will in just a sec. Okay, so these are the 4 possible games, right? What we're doing is we're just comparing these payoffs, right? And what matters is when they're greater or less than one another, right? So what we want to do is know, well, when is C greater than D? And when is C less than D? So up here, we have, up in this top half of the graph, C is greater than D. And down here, we have D greater than C, right? Same for A and B. So what we did with the stag hunt and the dilemma is we moved from this region to this region, right? So look at this. So let me put this in the same form just so you can see it. So here, A minus B is 1, and C minus D is -1. So you're here in the stag hunt. In the case of the prisoner's dilemma, these flip, right? So then this becomes a -1, and you're over here. If we flip these, then you're moving up the vertical axis, either from dilemma to conflict or from coordination to delay. So we saw the dynamics for coordination. Here's the dynamical scenario for coordination, right? For dilemma, we saw this too. So cooperation was A, defect was C, and what you saw was evolution pushing all the way to D. Right? Delight is going to look a lot like dilemma, just the arrows are going to be reversed, and it's going to push all the way to C. Conflict is going to look similar to coordination, except evolution is going to push you towards a mixed point in the center. So in the hawk-dove case, you're going to get a mix of hawks and doves. So when we think about this simple interaction between actor and recipient, such that both the actor and the recipient can play a strategy, and which strategies we play affect our payoffs, then we have 4 possible dynamical scenarios, right? Hamilton's scheme really only tracks the differences on this diagonal. So for Hamilton, you can move along this diagonal and get the evolutionary dynamics right, depending on whether the actor is paying a cost or receiving a benefit, and whether the recipient is paying a cost or receiving a benefit. So it can move along this. But what Hamilton didn't consider were these other 2 classes of games: coordination games like the stag hunt, and conflict games like the hawk-dove game, right? These are important ways of behaving, right? These capture important classes of social behavior, and they have different sort of evolutionary behaviors when we set it up like that. So the system is going to behave differently in the case of conflict and coordination, so we need to consider these cases, right? So what I've done with this move is just sort of complicate Hamilton's scheme by 1 move, right? Let's think about just 2 possible strategies. However, both the actor and the recipient can play those strategies, and they're going to affect the payoffs. So that's one, we've sort of made one move to make the situation more complex, right? And we've got these sort of two new interesting sorts of evolutionary dynamics to think about. Dynamics where Hamilton's scheme of classification doesn't work very well, right? So Hamilton was on the right track. This is just really pushing it one step further. Okay, let me pause there for a second and field questions if anyone has them.
Well, I'll do the same thing that I did before. I would love to hear someone sort of summarize where we're at so far. Maybe Nwang?
I got the end part where you drew the conflict, dilemma, and coordination diagram. And I get how the stag hunt and the prisoner's dilemma correlate to that. I just don't understand what the -1 I'm pointing, but over where you have dilemma, what a -1 would be.
Okay, so it's a comparison of these payoffs. So since this is C minus D, all this -1 is really saying is that D is greater than C. And then the -1 on this axis is saying that B is greater than A, right? So in the case of the prisoner's dilemma, we would say Y would be selfish, would be altruist, right? And so all we're saying is that if we subtract B from A, B is going to be greater, so we're going to get a negative number. So we're over here. And then same here, we're going to get a negative number, right?
Well,
so whenever B is greater than A and D is greater than C, we're in the dilemma quadrant.
okay.
The stag hunt flips these. So all of a sudden, A is greater than B, right? This side stays the same, but in the dilemma, we flipped this. And so we've moved from the -1 to the 1. That make sense?
For just the A and B, right?
Just A and B. Yes, the exact numbers aren't very important from a game theoretic perspective. What matters is which is better, right? And the idea is that, look, natural selection in unstructured populations is going to push you towards the strategy that does better. So what we want to know is greater than or equal to. And so this -1 is just a way of saying B is greater than A. This +1 is saying, nope, when you compare them, A is bigger than B. When they're equal, you fall on the line, and those are borderline cases.
So can you bring this back? So the overall point that I think you made in the paper is that and you made it earlier in this lecture, is that the way that we classify a behavior is going to be contingent on the way that your partner is also behaving, right? Like that's the general idea.
Yeah, that's part of it. Let me elaborate a little, right? Hamilton's scheme of classification does not account for the recipient interacting with me. It only accounts for me interacting with the recipient, right? What the recipient does is of no consequence to the fitness costs and benefits of my behavior, right? Now, when we take this game theoretic perspective, all of a sudden, what my partner is doing, like in the case of the stag hunt, does have consequences for my behavior, right? So if I'm in a stag hunt case, if my partner is cooperating, it looks like I'm choosing between spite and mutually beneficial behavior. If my partner is defecting, I'm choosing between selfish and altruistic behavior. But that seems odd, right? Altruistic behavior is supposed to be altruistic no matter who I'm interacting with. So Hamilton's account doesn't generalize to these games of coordination and conflict very well. So we need to think more broadly about the evolution of social behavior, right? Game theory provides us with these kind of richer resources for thinking about what my recipient's doing in response to me. And this is just a way of mapping out the possible evolutionary scenarios. So in a way, I'm trying to preserve the spirit of Hamilton's approach. He classified these behaviors to identify an evolutionary problem. My point, the classification breaks down in coordination and conflict games. But by recognizing we're in a coordination game rather than a dilemma game, we have some interesting insight into whether we're in this kind of dynamical scenario or this kind of dynamical scenario.
Mm-hmm.
So I'm trying to preserve the spirit of Hamilton's view by enriching it with this sort of the formal resources that have been developed since Hamilton first published.
Mm-hmm.
Is that clear? Should I move on?
Yeah, I think you can move on.
Okay. So this is all pretty formal. But I hope the sort of shift from prisoner's dilemma to stag hunt is clear, right? In the case of the prisoner's dilemma, altruism is always bad. It always should be selected against, and we need something else. We need some sort of positive correlation to get altruism to evolve. Over here in the stag hunt, cooperation is stable if you can achieve it. It's just risky, right? I have to trust my partner is going to cooperate too. If he is going to cooperate, I should definitely cooperate. But I'm not sure, so it's risky. The risk dominant strategy would be to defect, but then we both don't do as well. So that's a different kind of scenario. And that's why a lot of people, when about cooperation, especially cooperation in human ancestors, have started to shift their attention to the stag hunt, right? It looks like coordination was the game our ancestors had to solve, rather than the prisoner's dilemma. Okay.
Well, and so just both of those games are, if you're biased towards cooperation or you're biased towards altruism, both of those games are solvable, right? Like there is a place in the prisoner's dilemma that both sides benefit. It's just not biased in the fitness landscape. Is that true?
Yeah, that's a fair way to put it. I mean, in the prisoner's dilemma case, you need that R factor. You need that correlation, that relatedness needs to be sufficiently high for it to evolve, right? Relatedness doesn't have the same role in the case of the stag hunt, right? You can get the stag hunt evolving without relatedness.
Mm-hmm.
However, relatedness can help you try and jump this gap. So if you're in a population where everyone defects and hunts hare, if you and a friend team up and say, hey, let's both hunt stag with each other, well, then you could take off, right? So that would introduce, that's how positive correlation might help in the stag hunt. But it's a different sort of game because once we get everyone hunting stag, there's no stability problems there. There's no threat of free riding. There's no sort of subversion by selfish types. If everyone's hunting stag, you want to hunt stag too. You'd be foolish to go off on your own. Right? So these are sort of different sorts of games. Now, what's sort of interesting in the literature is a lot of people thinking about human evolution and how humans became the super cooperators we are. They've started looking more at these coordination games, right? So they're thinking less about Hamilton's problem of altruism and more about stag hunt scenarios, right? How do we achieve the kind of coordination we need to achieve to get cooperation off the ground? And that's a different evolutionary problem, one that doesn't quite fit well in Hamilton's scheme of things, right? It looks mutually beneficial in some ways, but it's not always mutually beneficial because it depends on what your partner is doing. Okay. thoughts, questions?
For the stag hunt, when you have both sides, like hunting hare in your scenario, why is that not mutually beneficial? If they're both getting at least, oh, I guess, no, I get it. One is getting less and the other is getting more. Okay, never mind.
Make sense?
Yeah.
I have a question. So like for the stag hunt and in all of these, the values you're assigning are arbitrary. They just represent that, for example, cooperation of hunting the stag has more value than hunting a hare.
Mm-hmm.
Do these values consider environmental influence on like your ability to do this? Like what if there's a mountain range that just keeps you from being able to access stag? You're naturally going to fall into hunting hare because it's the only thing there. Like, is environmental influence a factor in this at all, or is it just being like ignored and you're just looking at individual on individual interaction?
Okay, so that's a good question. It sort of raises a whole host of complicated issues. So let me sort of approach this slowly. So this is still very idealized in a lot of ways. One of them is that I'm just sort of presuming a kind of stable environment, right? So fitness obviously depends on the environment for every organism. And I'm sort of presuming here that there's a kind of stable environment such that the inequalities work out, that we're in a stag hunt scenario, right? But as you point out, that might not be the case. There could be predator and prey fluctuations. There could be geographical barriers, right? There's all sorts of things that might limit the strategies available to us, or they might make the payoffs change. So maybe hunting stag is really noisy. 1 out of 10 times we're successful. That kind of risk might lead us to all hunt hare, right? So how we incorporate environmental noise, certain sorts of geographical barriers, these are really interesting, hard questions, right? The idea is that given what we've done to understand the biology of some population, we might think that, hey, they have certain strategies available, and the payoffs for these strategies might be represented like so, and they might be in a stag hunt. If they're in a stag hunt, then this is the kind of evolutionary scenario we face. And we can explore how they might have solved the stag hunt problem of cooperation. But that, as you point out, I've backgrounded a whole bunch of issues about what determines these fitness values. And it's all the ecology, the environment, geography, that's going to matter, right? That might move us out of the stag hunt realm. It might limit the number of strategies available to us. It might expand the number of strategies available to us, right? So these are just 2 strategy games. You can do one thing or the other. A lot of scenarios, especially social scenarios, there's going to be more than one thing we can do, right? There's going to be more than 2 things we can do. There might be 10, 20 different strategies we could deploy. And then that just makes it more complicated.
Okay, that makes sense. So this is just like more of an ideal version because there's like an infinite possibility of possibilities. You can't possibly have an equation for all of it.
Yeah, so think of it this way. Hamilton made a very, very idealized model. And I'm trying to make it less idealized, but just by 1 step.
Okay.
Right? So all these problems you raise are important issues for any formal evolutionary model. What I've tried to do is sort of say, look, Hamilton made an incredible advance in thinking about altruism, but it was limited because it didn't think about strategic interactions. So here's how we might enrich it. Now, I've taken 1 step away from Hamilton's simple model, but the real world is down the block, right?
Yeah.
We're still far away from that. This is still very idealized.
Okay. Makes sense.
I have a question about that diagonal line you drew.
Yes.
So is that supposed to merge the 2 game theories?
So this, if we restrict ourselves to this little diagonal line, this is where Hamilton's classification makes sense, right? So Hamilton is thinking about this diagonal, right?
And then you added in the coordination on top of that?
Yep.
Okay.
So when you expand it out, right? So in a way, it's sort of just think about what I can do. If what I do is costly to me, right? I could be in, if it's costly to me and helpful to you, I'm in the dilemma range, right? If it's good for me and good for you, I'm in the delight range, right? In the case that it's selfish and spite are sort of interesting points near the origin here, right? So Hamilton sort of had altruism, selfishness and spite are down here on the origin, and mutual benefit is up here.
Okay, got it. Thanks.
That makes sense?
Yeah.
Right? You could think of it like, let's think about this. This could be altruism, spite, selfish, mutual benefit. But he wasn't thinking broadly about these sorts of cases where you could have coordination or conflict.
All right, yeah.
Could you show us quickly what the biases for a conflict game would look like?
So what the payoffs might look like for a conflict game?
What the payoffs are.
Sure. So let's see, where do I have? Let's do it right here. So in the evolutionary literature, called hawk-dove games. In the economic literature, they're called chicken or snowdrift games. They're all usually versions of a game of conflict. So let me use the hawk-dove terminology real quick. So the way the story goes, and this is due to Maynard Smith, who was a contemporary of William Hamilton's, right? So John Maynard Smith thought, all right, here's a game that we might think about for understanding animal behavior, especially conflict. I have two strategies: the hawk aggressive strategy, or the dove, the defensive pacifist strategy, right? When two hawks meet, they fight, and it's brutal, right? You might be competing over a resource and a water hole, some carrion or something, right? If you fight it, you might win, but you might get injured, and injury is really bad. So you might think that's negative, or just to keep with the conventions I've been using, hawk is bad. That's the worst. That's like a zero payoff, right? However, if you're a hawk and you play a dove, right, you get it all for yourself. The dove backs down, plays the pacifist strategy, you get it all, right? The hawk gets 3, doesn't get injured, right? So it's better than fighting a hawk, but the dove doesn't get much of the resource, all right? If two doves meet, they split, right? So two doves will split the resource, they'll play the pacifist strategy. Hawks will fight, and because of the risk of injury, that's the worst outcome. The best outcome is to be a hawk against a dove. You get it all. The second worst outcome is to be a dove against a hawk, right? So notice now, C minus D is 1, and B minus A is also 1. So we're in this in this conflict scenario. Let me just make sure I did this right. Yeah, okay. All right, so now think about this. So if your opponent's playing dove, what do you want to play?
Hawk.
Hawk, right? If you play dove, you have to split it, but if you play hawk, you get it all. In hawk, what would you prefer to play?
Dove.
Dove, right? Because hawks fight, it's brutal, it's very costly, so you'd rather play the dove strategy against the hawk, right? So, right, what you get are unstable endpoints, and what you're going to see is evolution push us towards a mix of hawks and doves. Just as you answered, right, it's best to play the rare strategy. If you know you're running into hawks, so if you're in a population full of hawks, play the dove, avoid the conflict. If you're in a population full of doves, play the hawk, win the resource. So what's going to happen is evolution is going to push us to some midpoint strategies. So it's going to be a function of the fitness values, right? So that's a case of conflict. Was there a specific, do you want me to say a bit more about that?
Well, I guess my mind is biased to try to say big picture things, right? So in all of these cases, your choice is to work with your partner or to not, right? And then the difference in each of these cases are the payoffs that whatever situation you're in give you.
Right.
And so it's the numbers, it's the number weights that you put in the boxes that determine whether it's a conflict game or a delight game or a dilemma game or a stag hunt.
That's right. So I mean, so I gave you the standard Maynard-Smith conflict story for Hawk Dove. So I mentioned another version of the Hawk Dove game is called the Snowdrift game.
Mm-hmm.
So this is salient for some of us in the Northeast right now. And that's, they just give a kind of cooperation version of the game of conflict, right? So the idea is that you and your interaction partner are driving down a road, going opposite directions, and you both come to a snowdrift, right? Mm-hmm. Snowdrift has to be removed. You both have shovels, and so you can both get out and remove the snowdrift together, or you could sit in your car and let your neighbor clear the snowdrift. But if you both sit in the car, the snowdrift's not going anywhere, and you're going to be stuck there for a while, right? So in this case, you've got an option between sitting in your car, which is the aggressive hawk strategy, and shoveling the snowdrift, which is the dove strategy. The idea is if we both cooperate, good, we both get 2. But the best thing to do is have your buddy or your neighbor shovel the snowdrift. I guess you wouldn't be buddies if you did this to them, right? Have your neighbor shovel the snowdrift, and you stay in your car. But if you both play hawk, it's better for you to get out and shovel the drift because you got to get to work, right? So that's a kind of cooperation style version of the game of conflict, mm-hmm. Right? So you can think about these in different sorts of ways. But what's interesting is that as we put into the game, you can be in different scenarios that have different sorts of expected evolutionary outcomes, mm-hmm. Right? In the dilemma case, there's a dominant strategy, defect. How do we work against that? Positive correlation between altruists. And you've got this stable midpoint, and what we want to do is try and push away from that. How can we push away from that? In the stag hunt, we've got this saddle point in the middle. How do we cross that fitness valley to get from defecting to cooperating? Mm-hmm. Right? So there's sort of different evolutionary obstacles by these sorts of different strategic scenarios.
And do those different evolutionary obstacles, are they going to shape what we call altruism?
Well, in a way, part of my point here is that altruism is a pretty limited category, right? It's only a thin slice of interesting cooperative social behaviors that we might want to give evolutionary stories for how those behaviors originated, mm-hmm. Right? And the sort of evolutionary story we give is going to be different if we're in a coordination or a conflict scenario, mm-hmm. Right? So it's more that, look, class of truly altruistic behaviors, we've got a ton of cool models of how altruism could evolve. Mm-hmm. But that's only a thin class. There's all these other cases.
I see. Yeah.
There's a sort of richer world of social behavior out there with different sorts of evolutionary obstacles that need to be overcome.
So in this framework, the word altruism really only applies in the dilemma scenario.
Yeah, down here.
Yeah.
I have one more question. Are there any situations where A minus B or C minus D are 0 and you're constantly flip-flopping between two of the categories? Like you're on the line, you're not in the corner?
Okay, good question. So you can be on the line, right? And the way I've been telling the story is that these are sort of presumed to be kind of static. Now, that might not always be the case. As you mentioned earlier, maybe there's a change in the environment, right? So there's certain evolutionary changes that might push you out of coordination into delight or from delight into conflict, right? Just by changing the payoffs available. You could be on the border or on this side, but on the border. So this would be a case where C and D are equal, right? So it's 1 and 1 and then 3 and 2. This is going to be an even easier case for cooperation, right? Because it doesn't, if my partner's defecting, it doesn't matter what I do, I get a payoff of 1, right? If my partner's cooperating, my choice is between 3 and 2. So in this case, when I'm on this line, you should cooperate, because in one scenario, you're trying to coordinate, and in the other scenario, it doesn't matter what you do, right? So on the line, it depends on whether you're here or here. Certain other sorts of dynamics are going to drive it. And also, the second point is that the environment may change so as to change these payoffs over time, setting these into stone, right? And part of the way biologists and social theorists have tried to solve dilemma questions, this is sort of an aside, is by introducing punishment. Non-cooperators, well, then you're changing the game, right? You're including sanctions, which is in a way kind of trying to transform the dilemma into a coordination problem. Now, punishment raises its own sorts of evolutionary puzzles, but that's one way you can change the payoffs, by forcing people to pay if they don't cooperate.
All right, cool. That makes sense.
Can you say a little bit more about that? That how in introducing this new, because I guess when introducing punishment, what you're doing is you're changing. It's no longer a binary behavioral option, right? Like you can cooperate, you can defect, or you can punish. And so
there's all sorts of interesting punishment. So notice what we've done is looked at 2-person, 2-strategy games, right? This is a very simple, narrow way of doing it. One way to expand it is to look at this game and to create a sort of second game off of the first. One game, and then based on how that game is played, you might have an option to punish. So this is often how punishment is introduced, right? So maybe you play a prisoner's dilemma, but then you have an option to pay one to partner if they didn't cooperate. That's just, so now we've got a 2-stage game. Now it's much more complicated, right? So really, there are 4 possible strategies now, right? Because you can cooperate or defect in the first round, and then you can punish or not punish in the second. Combinations now. That's a much richer game, right? So let me just, so I'd love to talk more about punishment, but I think now might be a good time to sort of, I want to point to how complicated things get. 2-by-2 games happens if we expand it to 3-by-3. All right. So far we've been looking at 2-person, 2-strategy symmetric games. There are 4 possible games. and then each possible game has a particular evolutionary dynamic associated with it, right? So what happens if we do 3 strategies? So both actor and recipient can play one of 3 different strategies, right? Any guesses on how many possible dynamical scenarios there are? Come on, just hazard a guess. So we went 2 by 2, we got 4. 3 by 3, how many?
9.
27. More than 27? Is what?
More than 27. It turns out there are 49. So let me show you this real quick. So this is so for a 3 by 3 game, this point was made by formal game theorists Imre Bomza and an enterprising graduate student at UC Irvine built a poster with all the possible ways the 3 by 3 strategy could work. So let me pull that up. Okay, so these are the 3 by 3 dynamics. 49. Okay, so let's look at this. You've got a triangle. Now, I showed you a line because there were 2 possible strategies. Now there are 3 possible strategies, so you're going to have a triangle. At each vertex, you've got 100% one strategy. If you're somewhere in the interior, they're present in the population. And look at all the complications that ensue, right? One of my favorites is number 9, where you get the spiraling towards the center, right? So that's 24, and there's the remaining 25 cases, right? So these are just looking at all the possible payoff combinations of the game and all the possible dynamical scenarios that result.
Wow. So, I mean, maybe this doesn't really matter, but could you say what the number, like, because my impulse was to like think about powers of 3, but like that was not like where does 49 come from? Is it just idiosyncratic, or is there some sort of elegant structural reason?
I bet there's an elegant structural reason. I don't know of it, right? So the way Bomza did it is he just started exploring almost, it wasn't quite brute force. He had sort of ideas about, hey, how might you introduce neutral saddle points into the 3 strategy simplex? Mm-hmm. And then he was coming up with all sorts of variations. He actually missed a couple. So some formal theorists have gone back and sort of realized that he missed a couple options. Is the product of Bomza's original work and some subsequent work finding the missed dynamical scenarios. So I think it's 49. Might even, I mean, it's sort of hard to say. And that's just the 3 by 3 case, right? And we were just talking about punishment, which gives you 4 possible strategies. So as soon as you start thinking about more realistic strategic scenarios, the dynamical complexity starts intractable. This is why we tend to focus on these sort of simple cases.
Right?
And it's why, so if you think about, that's just the 3 by 3 case. Wow, Hamilton was a weird genius in the 20th century coming up with a solution to the evolution of altruism problem. But even that, it's such a thin slice of possibility. Mm-hmm. A whole broad class of social behaviors that we need to think about.
So that gives me a bunch of questions. I guess the one for right now is there, when you were earlier talking about this that you put on the board, there are things there that resemble punishment or resemble spite was the term that you used, right? Mm-hmm. Like I think you were talking about the stag hunt, and you said that to not cooperate in the stag hunt looks like spite. But that's not the same, doesn't have the function of punishment in the way that you're describing it.
So punishment, let me back up a little bit and say some more about punishment. Punishment's a sort of fascinating strategic option for a lot of reasons. So first, it's a very sophisticated behavior because it's in response to something else. You think about punishment as a response to some kind of violation of a norm or some sort of violation of an expectation. You were supposed to cooperate. You didn't, I'm going to punish you. You were not supposed to park there. You did, so you got a ticket, right? So they're, in a way, they're sort of norm violations. So they're kind of very cool, interesting, complicated behaviors already, right? So in a way, to even have punishment off the ground, you already need a sort of foundation of social interaction to generate the kinds of expectations and norms that we can deploy and then react, violate them, that could be called punishment. So punishment is a kind of complicated behavior. That makes it tricky to think about how you might identify punishment in animal behavior, right? Because some cases there do look to be interesting cases of punishment, but there's this kind of cool definitional or philosophical or framing issue with how you sort of identify it. The other thing that's interesting about punishment is itself generates a kind of free rider problem, right? So when we think about the evolution of punishment, I want to live in a society and cooperate, but if someone doesn't cooperate, I don't want to be the guy that has to punish them because punishment is costly, right? And so you get the same kind of problem with costly behavior emerging about punishment. It's much better for me to just relax and let someone else do the punishing, right? Than for me to actually pay the cost to punish. So it generates, used, I think, sort of Bowles and Gintis and Boyd and Richardson, who have thought about the evolution of punishment a lot, put it this way. It generates a second order free rider problem, right? Because punishment is generating a public good, namely compliance with the cooperative norm. So punishment's cool and fascinating and weird and hard to wrap your head around from an evolutionary perspective.
And I guess also very difficult to model.
It is sort of challenging to model. So a lot of models do the simple, take the simple strategy that I've described, where you either cooperate and defect in a prisoner's dilemma or a public goods game, and then you have the option to punish or not punish. And then they look at different strategies that might evolve, and they do simulations and see what happens. Mm-hmm. Yeah, so punishment, that's a whole new layer of complexity. And often punishment is introduced to think about games that are repeated, which is another way of making this complex. So these are one-shot games. What if we play these games over and over again with the same partner? It's very different, right? There's a lot more strategies involved. Right? We can respond to defections from our partner by retaliating with defection. So thinking about the repeated games was an important step to solving the problem of altruism. That sort of takes things in a different direction that I've been talking about today. So triggers and reciprocal altruism and repeated games raise all sorts of new possibilities. So yeah, any other questions or thoughts or broad musings about social behavior?
Yeah. So it seems like the way that these problems are often framed, right, is like I guess because we have a moral bias, right? Like as humans, we have a moral bias. We like to see cooperation working, or we like to see altruism working because we were raised to think that way, right? And then you look at evolutionary theory, and it's just like altruism becomes this giant paradox of like it never should exist, right? If you're thinking of it narrowly in some sort of prisoner dilemma setup, right? So I guess I'm wondering what can this this model, this four, these four scenario model that you've just described, what can that tell us about the evolution of cooperation, just sort of in general, or like what the way that we should think about altruism, I suppose, from an evolutionary perspective?
Yeah, okay. So that's a good question. I mean, the obvious point, and this isn't a point that's original with me, this is just the way the literature's been moving, is that when we think about the evolution of cooperation, we should not limit ourselves to the altruistic version, right? So this is a transition that's being made all over the place, right? So let's not think about the dilemma, these sorts of coordination issues, right? And think about stag hunt issues. And so the idea is that, hey, you know what? In early human ancestor evolution, they faced problems of sort of collective foraging and collective defense. It was easy and obvious and just involved coordination, right? So they didn't face the kind of problem of altruism as it's traditionally conceived. The idea is that, hey, guys, there are big predators out there. Let's all team up and hang out together so that we can fight them off. Or, hey, let's share information about where to find tasty grubs and watering holes. Easy that it's kind of hard to defect on that kind of information sharing. If I tell you if I lie to you where the watering hole is, you're just not going to listen to me next time. So these sorts of collective defense and collective foraging tasks look than the sort of problem of altruism as it's traditionally conceived, right? So a lot of people have been focusing on these coordination issues, and they think, hey, that's how human cooperation got off the ground, right? It went on and got more complicated and interesting, integrated into human life ways. And then later on, we had opportunities to defect. And that's where you see the emergence of moral norms, right? So Kim Strelny makes this argument. Others make it an argument too, but in his book, The Evolved Apprentice, which I cite in that paper, he makes this argument that, hey, early cooperation was easy, and then once we became groups that would generate nice surpluses, that's when defections started to come up, right? And moral norms, Strelny, might have originated to help stabilize the system from this sort of early defection, right? And so the idea is that we didn't face the kind of threat of free riding until much later on. We developed kind of moral norms and punishments and sanctions as ways of discouraging that kind of free riding behavior that emerged once we became obligate group living cooperators. So it's really, in a way, this sort of helps expand our horizons for thinking about social behavior. Sort of changes the topic a bit from focusing about just on free riding and subversion to thinking about, well, let's think about coordination. Let's think about other sorts of cooperative endeavors that aren't purely altruistic. And that might be the key to unlocking the sort of general ratchet mechanism that might have produced the sort of impressive levels of cooperation we see in human societies.
Okay, so I have another question. This is even more vague, I suppose, but I guess this is a philosopher question, which is what in your mind is what is the best way to use a model like this? Because like you just showed us this like nice picture of like, okay, here's this 2x2. It's too simple. Let me expand the framework a little bit. But that's also really simple. Hey, look, here's this person who made like these beautiful triangles, and there's 49 of them, and we can examine all the options, but like still, like the world is full of more than 49 options. So like what role do models like this play in, like, I don't know, the way that academia works, or the way that we ought to work in the world, or like what's the function of a model? How's it
Okay. So that's quite an open-ended
yeah.
and big question. The function of a model. Well, let's these models might play in evolutionary investigation or evolutionary inquiry, right? I think even as simplified and idealized as they help structure the space of possibilities in an interesting way. They help us explore how certain kinds of social behaviors might emerge or originate, right? So what Hamilton did with altruism was revolutionary. He showed, hey, this kind of sacrificial behavior, help someone out, it can evolve under this range of conditions. That's really interesting and insightful, right? So what we're doing is just sort of expanding the sort of possible evolutionary scenarios for how different kinds of social behaviors might evolve, right? So this helps us structure the space of possibilities in a way so that when we go out and inquire about the evolution of real social behavior, we've got some grip on how things might have played out. Only a start, right? And part of the problem here, and this is sort of a big philosophical problem, is social behavior very rarely leaves any kind of fossil traces, right? Early human ancestors lived in groups. We do know they were probably involved in collective foraging and collective defense. And there's lots of evidence about group living. Their societies originated. Hard to leave traces when it's social behavior, right? So these models help give traction on how these sorts of things might have evolved. Mm-hmm. Within evolutionary biology itself, I think these models play an important role in kind of advancing our understanding of the evolutionary dynamics of social behavior generally, right? Even though they're simplified, even though they're idealized, we can start to think about new cases in ways that might hopefully one day provide traction on real cases. Mm-hmm.
Well, that's a really interesting point about the fossil record. If you've got a theory and you want evidence that your theory makes a prediction about the way the world is, and you want evidence about it. Like one way you can gather evidence is by digging in the ground, and then you pull up a bone and you say, "Aha! Here's confirmation that what I thought was true." But if you can't do that, then I guess these models can be some form of evidence production, that like you create a series of rules and you say this is how it works if the scenario is like this.
I would hesitate to go that far, right? Because I mean, look, if I had a general model of the evolution of social behavior, much like Newton's general model of terrestrial mechanics or something like that, right? Then we might be able to deduce laws and all sorts of cool things, and that might provide evidence. But this, I don't think these models will ever generate evidence in any kind of robust sense. What they'll do is they'll help us structure possibility space. Mm-hmm. But ultimately what we want is evidence that evolution unfolded like this in human ancestors, or in this lineage of primate, or in this lineage of mammal, right? And that's just going to take a lot of hard work. And social behavior is particularly difficult. I mean, all evolutionary inquiry has to sort of cross this epistemic hurdle, like try and reconstruct the past based on molecular sequences and fossil data, and all sorts of resources are available, but the traces are few and far between. Social behavior leaves even fewer traces than feathers or other sorts of physical adaptations. So all this to say, it's sort of difficult to do evolutionary inquiry anyway. It's especially difficult for social behavior, right? It's not impossible. Interesting work that's been done both in humans and in non-human animals, trying to reconstruct how societies must have been like, right? How big of a group did particular organisms live in, right? That can be a guide to what sorts of social behaviors we might expect to see.
So there's a few folks that we haven't heard from yet today. So I will do more cold calling. So Richard, what are your thoughts on all this? Do you have any questions or comments? I think you are muted. Oh. Oh.
Well, I don't really have any questions, but I'm kind of fascinated by the numbers with the three model, and kind of thinking of, how it came about and stuff like that. I don't really have any questions.
What about Melvina?
I don't really have any questions.
All right. Well, I guess we can call that an end, I suppose. Thank you so much for giving this presentation. I really appreciated the use of the board. Most of our speakers, well, all of our speakers actually, they sit in front of a webcam because this is an online thing, and having that extra visual layer, I think was enormously helpful. So that was really cool to play around with.
Hopefully it helped. I mean, this is kind of a lot of formal work. It's hard to sort of make it accessible without a lot of background, but hopefully you guys were able to get something out of it.
Yeah, well, I mean, so for me, so everybody in the class goes and makes a video, and I think what I'm going to be making this video about is just sort of like the expansion of the idea of altruism, because I think we get really fixated on because we have these like we have moral indoctrination, so we the word selfishness or selflessness or altruism or all of these things, like it whenever you bring it up, it creates some sort of emotional response. And so I really appreciate this because it gives a framework for using those words and talking about them without having the various like social norms that we need to abide by as humans ringing so hard in our memories when we think about these things. Or ways that cooperation can evolve, or working together can evolve, that don't have to fit into this like zero sum game mentality that we often think about in terms of what altruism is. So that's really cool.
Nice.
I feel like, so just going off of that, like you were saying how altruism is just kind of like a thin slice of cooperation. So I don't really know my question, but like, so behaviors that we normally call altruistic, would you say that they're not necessarily altruistic? That's just like, we call it that, but that's not necessarily what it is. It's more so, a game of cooperation.
Yeah, so I mean, this is kind of a tricky question, especially when we think about humans, right? So one point is that, look, if we think about it from this evolutionary perspective, there's a whole range of cooperative behaviors that are not strictly altruistic, and we should think about those, right? Because they raise these sorts of different evolutionary scenarios, and there's going to be different sorts of explanations for how those behaviors originated. This whole classification scheme is all based on sort of fitness, costs, and benefits. When we start thinking about human altruism, there's this important motivational or psychological component, right? It's not enough that people are paying a cost to give someone a benefit. It's that they've got to have the right sort of intention. Just doing it because there's some kind of Machiavellian that's calculating that they're going to get some favor in return, that doesn't seem like altruism to us. That seems like manipulation or selfishness or cold calculation. So there's this kind of motivational layer. And really what I've said today has been really focused on the evolutionary story, with the costs and benefits of the behavior. And when you ascend to this kind of more motivational story, it gets more complicated than that. right? And there's a whole host of literature and thinkers that have tried to discuss whether there's sort of genuine altruism possible. Really, ultimately, a kind of cold calculation that we're going to get a favor in return or something like that. I don't have much to say on this. Interestingly, so I mentioned, so William Hamilton, who came up with the earlier classification, he worked with another sort of fascinating genius named George Price. And George Price ended up, after doing this work on evolution, worrying about whether true altruism was possible. And those worries eventually drove him to suicide. He was not mentally balanced. It was a very tragic way to die. But he was worried about these problems. He thought that the evolutionary story undermined the possibility of true altruism and this crisis of faith in him. So there's all sorts of cool things you can think about along these lines. And nothing I've said really makes traction on that human notion of altruism. So that was sort of a long answer, but I just wanted to sort of add that there's like a whole layer of complexity here. I'm trying to steer clear of it, but it's there and it's very important.
Gotcha.
Yeah, well, because it's, I guess this thing happens when theorists start using words. The words maybe pull away from the ways that we normally use them in social English.
Mm-hmm.
Right? Like these are like coordination is down there in the bottom right, but really in sort of all of these things are questions of coordination. It's like what are the conditions that will allow coordination to happen or not? And maybe that's a better word than altruism, because altruism has these moral weights to it.
Yeah, and that could ultimately, like, it was sort of a puzzle, an evolutionary puzzle, and I don't think Hamilton, he didn't coin the term. I mean, Darwin was worried about altruism. Other evolutionary thinkers were worried about altruism, but it does have a kind of very particular connotation in the human case that potentially it's too distracting. Maybe that might be worth exploring as a kind of historical hypothesis. I have no idea. I would turn to a historian of science to ask that question, but cool things going on there. And maybe that's the case, right? That this sort of export of thinking about altruism in a moral sense to thinking about it in this weird theoretical biological sense, maybe there's some baggage that came along for the ride.
So I have a question. So when you talk about altruism, would you equate that to selflessness? Or like I know here it's like it's either an altruistic behavior or a selfish behavior. So then would that be selflessness versus selfishness here? Or are those two terms you're going to consider them different?
Well, in a way, I could see how that could map on. I mean, so biologists like to think in terms of fitness costs and benefits because they want to look at social behavior and like we don't want to restrict ourselves to psychologically complex animals like ourselves, right? There's a lot of research on microbial altruism, right? They're not very complex, cognitively speaking, right? So, but they can behave altruistically because they might be paying a cost to help out their neighbor. So in that case, I guess it's sort of selflessness because they're giving some of their self to their neighbor, right? You could think of it that way, but ultimately, have selves. I mean, biologists don't want to tangle with those sorts of hairy philosophical questions. They just want to try and think about the evolution of social behavior. And, bacteria can be social by interacting and swapping plasmids and trading lots of other ways, right? So they've focused on the costs and benefits so they can have a general picture that can apply across the biological realm, right? When we move it to us, that's an interesting question. Maybe there is something to it that altruism is a kind of selflessness. Oneself paying a cost to help someone else out. I think there's something to that.
Because in biology, when we talk about altruism, I know in ecology, cost to yourself to benefit the other party, but you would usually do it in an altruistic behavior with someone you have some sort of relatedness to.
Mm-hmm.
So in that sense, it's somewhat selfish because you're benefiting yourself by helping the other party. But when I think of like selflessness, I think of a relationship like you having a cost without necessarily having a benefit to yourself, just helping the other party.
Mm-hmm.
So in that way, like I like see those two things as like different.
Yeah, interesting. I guess it sort of depends on how you want to think about the benefits accruing, right? So when I behave altruistically in a kind of biological sense, am I really kind of like accruing more benefit down the line? Well, maybe if I help you out today and you help me out tomorrow, I am. But maybe we have that act of helping people that know the secret handshake or have the right signal. Maybe that behavior persists in the population. So maybe I don't benefit, but maybe my offspring benefit, right? Then it might be a kind of pay it forward style of altruism where I myself am not directly benefiting. Maybe I'm indirectly benefiting because my offspring and progeny benefit. But there's kind of an interesting scope ambiguity here about how we want to sort of measure the costs and benefits over time.
Right. Like I just thought of something like, let's say you have a pet and that pet is about to get hit by a car, and you go and save him, or you save the pet, and you ultimately like give up your life to save your pet's life. In that sense, you have a relationship with that organism. But then, like in a case where you see a squirrel about to get hit by a car and you like go out and try to save that squirrel, you have no relationship to that squirrel. And I don't necessarily think that squirrel is going to do anything to help you.
Nope, probably not.
Or so I see the first scenario as altruism and then the second scenario as selflessness, because there's just like no benefit that you can get from that. You just died.
Yeah, that would be that sort of behavior you'd expect to go extinct pretty quickly.
Yeah, well, that's the other sort of thing. Is like we have biases to thinking about these behaviors in terms of like the scale of a single life, because that's the scale that we operate on. But these models are designed to talk about dynamics over hundreds or thousands of generations, right? So it's a shift in the way that you're thinking.
Hmm.
Well, I think we can wrap up here. Thank you once again for this lecture. There's quite a lot to think about, and I really appreciate your time.
Yeah, no problem. I hope it was useful.
Yeah, so I will send you the work that the students do when they've completed it next week, and we will go from there. Yeah.
Excellent. Thank you, Maximus. Thank you all. Have a great afternoon.
All right. Farewell.